The other principle we can take advantage of is conservation of momentum, and here we're going to talk about translational, so we're not going to worry about the part rotating about its own center of mass. We're going to treat everything as particles right here. That's one of our assumptions, everything's a particle. And you think that makes, so particles is another assumption. So you can think about it, it makes sense. Repetition use momentum every time I have things colliding and there's this impulse given from one to the other part. And so whether it's they start out together and they repel each other, or they have a collision, unless it's elastic, which is saying there's no energy loss, then we can't use energy. And so most collisions, interactions, things like this are not going to be assuming no loss of energy, but momentum holds true. And momentum is also powerful because it's a vector quantity versus energy, which is a scalar. So we're going to think about these two. We have these two particles. One's the bullet, one's the person in the gun, and there's some force between them. And kind of think about right here, we're going to have this pressure force, which is building up in that chamber. So from the time the gunpowder ignites and pressure starts to build and pressure starts to increase, the net force is acting on that from that pressure force, or also even from the frictional forces. This has some frictional force on the barrel. It has this equal and opposite frictional force on the bullet. So that kind of that impulse is whatever there, the negative value, the same absolute magnitude is given from one to the next. So momentum is something we're going to use here, and we're going to consider from the time that pressure starts to build. And then on the problem statement is we're told that the moment that bullet exits the barrel, we have a velocity vb at this angle. So we're going to have our final time be when that bullet finally exits the barrel. So now we have talk about what we're going to have. We have these two particles. The first particle is the bullet. So we'll draw a feedback diagram in the bullet. So it has we have this force from the pressure acting on it. We'll assume drag forces are zero. We'll assume that there's no air drag here by the outside environment acting on that. We'll assume that's zero. When we have gravitational force, and then we'll have a buoyancy force. I always draw a buoyancy force in there often for something moving in air, that you can always assume that it becomes zero, because just like gravitational force is the mass, which is the density of the bullet times the volume of the bullet times g. The buoyancy force is the density of the fluid that's displaced, in this case, which is air, times the volume of whatever the bullet is times g. Well, the density of air in our normal surroundings is about 1,000th that of the density of water, and the bullet's probably going to be 8 times more dense than air. So this term is probably 1/81. Yeah, so much less than 1,000th of that. So we'll assume that goes to zero. So there's my feed value diagram of the bullet, feed diagram of the person and the gun. So what's all the forces acting on that person in the gun? Well, the rope is applying a force to that person in the gun, so I have a force there. I have that same pressure force shown in the direction shown. I have the gravitational force, the mass of the gun plus the mass of the person times g. Again, the buoyancy force, which I drew in there, but again, we'll assume that the density of air is much less than the density of the person in the gun, so we'll assume that potentially goes to zero. So I've drawn every single force that's acting on there with considerations of what I assume to be approximately zero. Next question is, what's the coordinate system? Well, anytime I have something rotating, it's often very convenient to pick the center rotation is the point where I want to do it, and then kind of often it's easiest to have from that particle to the center rotation, call that either, if the guy's over here, then I would say, I call that a direction to that center. That's a very convenient thing, because then you can either you can have whether you want to call it the x direction, the y direction, or the parallel to motion perpendicular, or the r and the theta. That's a very convenient coordinate system to often pick. And you can always, even you draw it next to the part, you can often think of it's at the center of rotation is the kind of thing. There's a grid attached to the Earth that's fixed, that's not moving with the part, but at this instant of time, that grid has I'll draw these coordinate system right there to help me write my equations easier. Okay, so in this case, we're starting out and he's hanging straight down, and so we'll have our whether we call r theta, parallel perpendicular, xy. We're gonna do it in just this simple direction right here, and often drawing is important because which is the positive direction of it. So we're saying that's the positive x goes this way and the positive y goes that way. So now from this we can write our equation for momentum, and so momentum is a vector quantity. So we're in the positive x direction. So I'll put x colon and then an arrow and showing everything here means positive. We know the change in momentum of this system in the x direction with respect to time. Well, that's the net forces. We're going to assume that gamma is 1. The velocity of the bullet is much less than the speed of sound in a vacuum, and so gamma is 1. We assume that there's no change in mass as this bullet is going through here. So we can so momentum is mass times the velocity. The derivative of this momentum, we'll say mass is constant, so that's mass times the derivative of the velocity of this bullet in the x direction with respect to time. Well, that term is acceleration. So anytime we're going to have a problem where we're going to assume the mass is constant and gamma is 1, this change in momentum in the x direction versus time is going to turn out to be the mass times the acceleration of that mass, the center of mass of that part in that vectorial direction. Well, that's the net forces in the x direction. These are y directional forces. The only force that acting in the x direction is the vectorial term of this pressure force, V sub p, is acting in the minus x direction. I define x positive that way, minus fp cosine theta. Okay, so here's my resulting thing. I get my mass, change in velocity in the x direction of this part is equal to the minus the pressure force cosine theta. Okay, now we can jump to this term over here. Again, we talked about all the forces, the pressure force, the rope force. Again, we can pick a coordinate system. I'll pick the same coordinate system again because he's hanging straight down. So these kind of they're all exactly the same because there's no rotation at this point. And these, positive x direction. So positive x direction, again, change momentum in the x direction of the system with respect to time. Gamma is 1. So mass is constant, so that's this mass times the derivative of the velocity at the center of mass with respect to time, and that's the net forces. The only net force at this moment of time, when everything's hanging straight down, is the vectorial component of this pressure force. That's a positive this time, Fp cosine theta. So very similar here. I did sum of forces in y right here. That would tell you information about the acceleration in the y or the rope force, but we don't really need to solve for that because we get every information we're going to get from the x. So we'll kind of just focus on everything in the x direction because we're going to see that's going to give us lots of valuable information. So here's this term right here again for the bullet. Likewise, I have the similar term for this net mass times the change in velocity in x direction of that part is this term right here. So here's my equation. If I take the derivative of, this is the derivative of x with respect to time, I know my initial state, nothing was moving. So before this went off here, I had in the x direction, my bullet had 0 velocity, and my gun and my person had 0 velocity. So I know at the beginning of my time, initial time, it was 0. I was told that at the end of time, the instant that this is leaving the chamber, I have the bullets traveling at this velocity, so that's its final velocity. So I have this information about delta velocities. So I can think about taking the derivative of this, the integral, sorry, of this term. So that's going to be my delta velocity of the bullet with respect to x. That's my impulse. That's my force, which is my FP cosine theta, alpha, excuse me, with respect to time. So impulse over this mass. So that's my change in x, and we know that x initial is 0, so that's really my final velocity of the bullet in the next direction. And likewise, here the only force acting in the next direction in this, luckily with this case, was this FP cosine theta. So I got a very similar term from this and that. Okay, so there's my term. I take the integral. Okay, the change in the velocity of these parts with respect to x. It is this impulse divided by mass. And you can see that this term right here and this term right here, well, they're the same magnitude. They're just one's a plus and one's a minus. So the impulse that was given to this, which has the change in velocity times this mass, if I brought this over here, is the same as this impulse over here results in a change of velocity of the person times the mass of the person. And that makes sense. So I have just these two things interacting, and whatever impulse goes to this one, the negative goes to this one, and this at the beginning of time, the center of mass is right here for both these parts. The bullet's going to be racing off a lot faster than this one's moving, but because of this relationship, and that's all the forces I have acting on this part, there's no other force. So I know in the final condition, the velocity of the person and the gun in the x direction is minus the x direction component of the velocity of the bullet finally, and times the mass, so mass of the bullet divided by the ratio there. So that's just the equation, just solved algebraically. We know, I was told that the velocity of the bullet in the x direction finally is the magnitude of total velocity, v sub b, and that's the cosine part. So I know that in the x direction at this final time when the bullet leaves the gun, my velocity of the person in the gun in the x direction is this equation right here. Now that hasn't answered the final question, but that is at that time when they're no longer interacting. Now I know the velocity of the person in the gun in the x direction.